Okay, let's get started. Before I start talking, we have an announcement.
Hi, I'm here from Women in Computing. I'm the vice president. I just wanted to invite people to Women in Computing pre-major social. It'll be this Wednesday, 4:30 to 6. Its focus is being a woman in computing, but everybody's welcome. They'll be food, so feel free to come. It's the room right next to the school computing. So, hope to see you there.
I notice it's cleverly timed to start right after this class ends.
Oh yeah, exactly. It's on purpose. So.
Okay. All right, so PS7 is out, as it has been for 2 weeks, but it's finally coming due this week. Any questions or problems with PS7? Okay, the midterms are graded as of about an hour ago. You can see your grade on Canvas, but what you want to do is go to GradeScope and you can see your exam, the scanned exam, and you can see your grade, the breakdown of the grades. For each problem and subproblem, you can see the rubric and figure out what you did right, what you did wrong. There is, in GradeScope, there's a feature where you can request a regrade if you think we made a mistake. So the thing to realize is that the regrade request goes with a particular problem. So it's not like you go fill out a massive regrade request and submit it. You go to the problem, say it's problem 2.1, you attach the request to that. And if you have another one, you attach it to that other problem. All right, any questions about that or anything else? Yes?
How do you access that at grade school?
How do you access what?
The midterm at grade school.
Alas, I don't know because I'm not a student. How do you access?
Click on it, and then it has a scan of your exam.
Grade school. Got it.
Okay. Yes.
So I noticed for all the coding problems, there were explanations, everything there. As far as certain ones where there was bubbles that have multiple answers, there really wasn't a breakdown of that. Will we just get those in lab tomorrow?
Yeah. We'll discuss. So to some extent, you can figure out. There's the rubric. The rubrics for each problem will help you see what the right answer was, but not always. I did post a solution. It's in the schedule right next to tomorrow's lab. And in lab tomorrow, you'll be discussing the solution to the problem set. The midterm. Anything else? Yes?
What was the midterm class average?
The median grade was 78, the mean was 76. The grades ranged from a high of 99 to a low of much lower. Anything else? Okay, so long time ago, right before fall break, we started talking about implementing classes, creating new types of data. And that's what PS7 is about. And I warned you at the time that you might forget a lot of what you learned that week by now, because in the interim you've had fall break and you've had midterm week and haven't been thinking so much about chapter 7 or week 7, PS7. So we're going to back up a little bit and try to remember what went on. So we'll start doing that here. Okay, this was actually a question on one of the sample midterms. But if you, my glasses just broke. If you see something like that in a program, and I tell you that F is a static method, then what does that thing have to be?
Class.
Right, it has to be the name of a class. So it might be math.squareRoot. Math is a class, square root is a static method in the math class. Integer.parseInt. ParseInt's a method, Integer is the class that it belongs to. Method library dot is palindrome. Class and method. So that's, you're very familiar with that for most of the semester, static method call. Okay? Now, if I tell you that f is an instance method, in other words, a non-static method, what does thing have to be in that case? Yes?
An object.
Has to be an object. And again, you're familiar with that from the standpoint of just using methods. Like if S is a scanner object, then S dot has next double is a object dot method name for instance methods. List dot add hello, or we're adding hello to a string list, an array list of strings. It would look like that. Random number generator, rand is a random object, then rand dot next in of 100. You're calling a method, you're invoking a method on an object. Right? That should all be very familiar stuff. Now, what's the list of all the parameters that are passed to square root? In that right there. Yeah, 3.5. Okay, there's one parameter, it's 3.5. Okay, what are the parameters here? Yeah, string 52. What about here? Yeah, the string rotor. That's all easy stuff. Now, what about here? What parameters are being passed to has next double? Yeah.
The object S.
Okay, he said the object S. Now we're used to seeing the parameters in the parentheses, but we call S right there the implicit parameter. Because after all, if we just say has next double, we don't know what scanner we're asking about. There can be a million scanners out there. We need to know which scanner you're asking about having a next double. So effectively, S is a parameter to has next double. It tells has next double which object it's operating on. And but it's not in the parentheses, so that's why I call it the implicit parameter. It's not always mentioned, but it's really there. Okay? So those, you might think has next double takes no parameters, and I would often say that, but in reality, it has an implicit parameter. What about here? What are the parameters to the add method? Yeah, the list and hello. If you're going to add a string to a list, you've got to say what string to add. That's the hello parameter, and you got to say what list to add it to. That's the implicit parameter in front of the method. What about here? Yeah, we got the rand object and 100. So I'm just trying to get you used to this idea. You've seen this all along whenever you've used instance methods, non-static methods. But the object is the implicit parameter to the implicit parameter to the method. So that's the difference between static methods and non-static methods. There is no implicit parameter for a static method. Now let's look at this. I have a class C, and it contains a static method called f. And inside f, I'm calling G and H. And I'm just telling you that G is static and H is not. H is an instance method. G is static method. Okay? So typically you say class.g to call a static method. What happens when you leave the class off? You just say G. Where is Java going to look to find G? Yeah, it's going to look in class C. So whatever class that the method call appears in, it's going to, if you don't say look in some other class, it's going to look in class C. So that's in this case, there's an implicit class. Now what about that H there? No object was provided to, and we're not, it doesn't say what object we're invoking H on. So what'll happen? Yeah.
This goes
This is a good guess, but there's a problem. This refers to the object on which the method was invoked. On what object was f invoked? Or if you were to call it, what object would it be invoked on? Is there an object on which that you can invoke f on? No, it's a static method. So that's a compiler error. You can't call an unqualified instance method from inside of a static method. So that's no good. So the C is implicit, but there is no implicit object in this case. Now let's change this slightly. I'm going to make this method no longer static. So all I changed was f is now static, non-static instead of a void. So to which class what's the implicit class for that call to G? Yeah, same as before, C. So it's really C.G. Now what about H? Is it legal to call H in this case? Yeah, I'll tell you the rule. The rule says that if we make an unqualified call to an instance method inside of another instance method, then the implicit parameter of H is the same as the implicit, whatever the implicit parameter to f was. So if we invoked f on some object, we're also invoking H on that object. Well, what is the object on which f was invoked called? Yeah? This, right. So that's what we have going on here. So inside of a non-static method or inside of a constructor, this refers to the object on which the method was invoked. So in this case, this refers to the object on which f was invoked. So when f is called, it will be invoked on some object. That's the implicit parameter. Inside of f, you can refer to that implicit parameter with this. And when you just make a naked call to a non-static method, unqualified, implicitly you're making a call on this. You're invoking H on the same object that F was invoked on. All right, so that's the relationship between, another relationship between static and instance methods. Now, I'm gonna break out of the slides now and go look at some code that we did almost 3 weeks ago. I guess it is 3 weeks ago. All right, we implemented a class called MyList. And you look at the comment there, it says, it's described, so when you create a class that's designed not just to contain static methods, which is designed to create a new type of data, your Java doc should say what the new type of data is that is being provided. So if you're used to writing Java doc for classes to say something like, this class contains methods for thus and such, that's appropriate when the class consists of just static methods. But in this case, we're creating a new type of data, and so we give different Java doc. So we're saying that a MyList is a simple dynamic list of integers. A MyList contains 0 or more integers that can be accessed and changed via a 0-based index. It is possible to add new elements to the end and to remove elements from the end. So we're just describing to whoever might want to use this class what sort of new objects are made available by it. So that was this class MyList. And you remember the methods that we had. First of all, we had a constructor here. So we have a 0-parameter constructor called MyList. We have a method called get, a method called set, add to the end, and looks like I left out remove, which I advertised, and size. Those are our methods. When we did this, we started with empty method bodies. What was the first thing we had to do? What was the first step of implementing the class? When we started 3 weeks ago, I the class here, but all the methods in the constructor were just stubs. Before we could fill out those stubs, what did we have to do? Before you can implement a cache class, which is one thing on PS7, there's something you have to do. Before you implement cache list, there's something you have to do. And before you implement the MyScanner class, there's something you have to do. Yes?
Create instance variables.
He said create instance variables. Okay, that's one way to put it. I would call it design a representation. Design, you got to decide how it is you're representing the new objects. Every object will contain within it instance variables that you declare in the class. You got to figure out what instance variables you need. And you see right here, there's only one instance variable. It's an array of integers. It's called data. And I have JavaDoc here as well. And I expect you to use JavaDoc to document your instance variables, because that's the crux of implementing a class, is coming up with a good representation strategy. This comment says holds the element of the list. So that tells us that array will hold the elements of the list. Which list? How many lists are there? Is there one list? How many array lists are there? Many as you create. Same thing is true here. There can be 0 MyList objects in a running program. There could be 1 million. So when I say holds the elements of the list, which list am I talking about of the millions you could create? There's just one variable there. How does it work to have one variable for 1 million lists? Yeah?
Objects, each variable, or each object has its own instance of that variable.
Right. They're called instance variables because every object ends up with an instance of that variable. So you create a MyList object by calling the constructor. You create an object that contains within it a data variable. You create another MyList. You have a different object holding a different array inside it. The third one, the millionth one, they all, if you create 1 million objects, each of those 1 million objects contains within it instance variables. So when I say holds the elements of the list, I mean, if I'm saying that if you cut an object open, you'll find within it an array called data that holds the elements of that list. But every list has its own copy, its own version, completely independent of the others. That's what we get by not declaring it static. If we declared that thing static, there'd only be one variable shared by all objects. And that's clearly not what you want. You can't have 1 million list objects all using the same array to keep track of their elements. They'd clobber, they get in the way of each other. All right, and I try to be more specific. So I say is exactly the same length as the list. So I'm just saying that if there are 10 elements in a MyList object, there'll be 10 elements in that data, in the array that it contains. And element I of the list is stored in data I. So I'm saying that you can index into a list. I'm just saying if you want to know what's stored at index 0, look at the element 0 of the array. Now, and so on. It doesn't have to be that way. We could be perverse and store element 0 at the end of the array and store the element size -1 at the beginning of the array. We just reverse the order of the array. Okay? That would change our code then. Our code would have to be aware of the fact that the array is reversed from what we were doing originally. We could make it work. But there's no reason to do that here, so we just have this simple representation. So before you can consider, before you can consider implementing MyList and get and so on, you've got to decide how you're going to represent objects. And until you have declared your instance variables and and know enough about them to describe how they work with a comment, you've got no business implementing any stubs, because all those stubs have to cooperate to maintain that instance variable. So a lot of students don't believe me, and they just want to dive right in and start writing code. And you can't. You can't implement a class until you've nailed down the instance variables. There's just no way. Go back where we were. Okay. So this is what we're just looking at an eclipse. There's MyList. There's the instance variable, private int array of data, and we see that the description of what that array is for, what it does for us. Now I'm going to ask you some questions to see how well you understand this design right here, this representation strategy. So suppose that you cut an object open and it contains the array 1592, or you look at it, you've got a MyList object and you look at it in the debugger and you see that it contains a data array and you see that it contains 1592. What MyList is that? What MyList does that stand for? What elements are in the MyList object that contains that array? All right, let me ask a more specific question. How many elements are in the MyList object that contains that array? 4. And what are the elements? 1592, in that order. It's a simple representation. So, So I'll draw arrays with the square brackets, and I'll draw MyList with the braces. But you see, if you can't answer questions like this, you don't understand the representation well enough to start writing code. Okay? Suppose you look inside an object and it contains an empty array. What does that tell you about the MyList object? It's empty. Right? Suppose you see that. What is that? If that's the array that a MyList object contains, okay. What MyList is it? How many elements are in that MyList? 2. 9 and 2. Okay. So you need to be able to, let's say if you're using the debugger, you're not going to see necessarily anything like this. What you're going to see is this. You'll see an instance variable that contains that array. You've got to be able to mentally map it to the MyList object that it represents. Now, let's go the other way. Suppose you've created a MyList object and you've inserted 4, 3, and 8 into it. What array would you expect to find inside that object? An array containing 4, 3, 8. Suppose you have that situation. You've created a MyList object, but you've inserted nothing. What would you expect to find inside it? The empty array. Suppose you've created a MyList object and inserted a 3 and then inserted another 3. What would you expect to find inside it? Yeah, that array. Now, we implemented MyList version 1, using this representation, and we got it to pass all the tests. We implemented all the methods correctly. What was wrong with it? Why did we go for version 2? Yeah.
It was really slow.
Yeah, it was really slow. Took, I think it was like 14 seconds to insert 100,000 elements, which is kind of slow. So we went for a different implementation. So I want you to realize we did not change the name of the, well, I guess we did, no, I don't think we even changed the name of the class. The method stubs were all the same. The Java doc for the methods in the constructor were all the same. What we have to change, what's the key thing we changed in moving from the first version to the second version? Yeah?
If I remember, when we copied everything into a new array, instead of it having to just add one more place, it would actually just double the size of the array
Okay.
every time.
So I'll generalize what he said. We changed the representation strategy. We decided, no, the culprit is, we always, every object contains an array that contains exactly the elements that are in the array list. And when we go to add one more element to the MyList, when we add one more element to the MyList, we had to make a copy of the array that was one bigger and then put the new element in it. So we just spent all our time making ever longer copies over and over again. And we decided a better strategy would be to make the array oversized, make the array bigger than we need so that we can insert into it until it fills up. When it fills up, we'll double it in size and copy everything over so that we don't have to copy so often. And that turned out to really speed things up. And these were the instance variables we ended up with. We ended up with two instance variables that cooperate to represent the state of a list. First of all, we kept track of the number of elements in the list. So you create a MyList. At any point, if you look at the count instance variable, it's going to tell you how many elements are in the MyList. Now, why didn't we need an instance variable like that in version 1? How do we get away without a count instance? How would you know? So we'll go back to this representation right here. How would you know how many elements are in a MyList object with that data array? Yeah.
The length of the array is the same as the number of, like it corresponds exactly with the number of elements.
Right. The length of the array is the same as the length of the list. So you just look at the length field of the data array, and that's how long the list is. But in this new version, oops. Too far. In this new version, we're going to keep count's going to be the number of elements in the list because the length of the list is not the same as the length of the array. All right, good. Yeah. Then we still have an array called data, but it's serving a different role. Look at the comment now. It says the elements in the list are stored in data 0 through data count -1. And the length of data must be greater than or equal to count. So what that says is that there can be room to grow. Maybe the list contains 5 elements and the array contains 16 elements, or let's say 8 elements. So that means the first 5 elements of that array are the ones we care about. The last 3 is just space to grow. That's what that comment is telling me. So if that's the deal, suppose you're using a debugger for the second version and you look inside an object and the data array contains 1592 and the count is 3. What list is that? First of all, how many elements are in the list? Not 4. Three. Count is 3. So we know the list contains 3 elements. Which 3 elements? Are 1, 5, and 9 in the list? Is it 5, 9, and 2? 1, 9, and 2? What was our plan on the last slide? Where do the elements that we care about reside? Yeah? Yeah, it's set from 0 to count -1. So it's the first 3 elements, basically. First count elements. So that represents the 1, 5, and 9. Well, what about the 2? What if we change that 2 to an 8? Would it change our answer? No. It doesn't matter what's stored in that last element of the array. It's not participating in representing the list right now. It's just room to grow. It's room for future storage. So it doesn't matter what's stored there. Okay? What about this one here? What list does that represent? Okay? What's wrong? Why is that a bad question? If I ask you what list that represents, what list does that represent? You need to ask me something. What's count? Okay, count is 0. So what list is that? Empty list. Okay? The count says 0. That's just room to grow. The 8 and the 2 don't matter. That's just their room to grow. Maybe the 8 and 2 used to be in the list and they got removed. And that's why they're there. They're not physically removed. It doesn't matter that they're there. It's just there. So we got a place to put something when something is added to the list. So that's the empty list. What about that one? Yeah? That's what?
Would that throw an out of bounds exception?
Well, it's just something. He said, would that throw the out of bounds exception? It's something that if you correctly implement your class, this could never occur. Right? Because when you implement your methods, you got to be sure that you follow the recipe in that Java doc for the instance variables, and it would not allow this to happen. Yeah.
Oh, it's going to be 9 and 2, and then the last index is going to be empty at the moment.
Right, but it's that situation should not arise in a correctly written program because the length of data must be greater than or equal to count. You're bound by that when you write code. This comment is unusual. Usually when you write JavaDoc, it's for the benefit of the client of the class. The user of the class doesn't care about the details like that. Who is that comment for? It's for you, the implementer of the class. And I have you do it in JavaDoc so you can easily, hover your mouse over data and remember what the rule is. So the idea is that's just illegal. It should not happen if you implement your class correctly. If it does occur, then you've done something wrong. That's a bug. Yeah.
So when we did the second list, and it would go ahead and the expanded point where it would double the array, so we have the extra space. Would it not look like something like the last example, where it has the elements of the array, but then it would have empty ones that are going to be filled?
Okay, so in the add method, let's say you suppose you had data was 9, 2 and count was 2. And then someone said, okay, add 7 to the list. So what's going to happen is your code is going to have to add 1 to count, and then it's going to have to double the length of the array and put a 7 in it. So temporarily inside the method, you might get a case where count has been incremented, but data hasn't been expanded yet. And that's okay. It's just when the method returns, then everything needs to be balanced. So illegal representation. Now let's go the other way. Suppose that's the list 438. Okay, if you create a list, if you have a list that contains 4, 3, and 8, and you look inside it at the instance variables, what are you going to see? What will the value of count be? 3. What will the array be? It'll start with 4, 3, 8. Okay? Might it contain other elements? Yes. But they don't matter. So I just wrote it that way. Data 4, 3, 8 and count 3. But it could have been data 4, 3, 8, 7 and count 3. As long as count is 3 and data begins with 4, 3, 8, that's a legal representation. Okay? Here's another one. Same abstract object. In both cases, the list contains 4, 3, and 8. But in this case, we're representing data has 6 elements for some reason, but count is 3. So that's just telling us only pay attention to the first 3 elements. Okay? And what could represent that? Count's going to be 0, and data can be anything, according to our representation strategy. All right, so I'm just trying to get you thinking in the right way here. When you implement a class, you've got to distinguish between the concrete values, which are the values of the instance variables, and the abstract value, which is the illusion you're trying to provide to your user. Your user is thinking in terms of lists. You're thinking in terms of count and data. You got to make the two match up. That's where the coding comes in. So let's go look at MyList 2 here. Okay, so you've, I showed you that on the slide, the instance variables, count, and data. So look at the constructor right there. It says right there, creates an empty list. Now, I want you to notice carefully. It does not say stores 0 in count and stores an empty array in data. The Java doc for the methods and for the constructors of a class need to talk abstractly. They do not talk about the instance variables, because instance variables can change. I mean, how weird would it be to go read the Java doc for a scanner class and find a detailed description of the instance variables used to implement the scanner? That's too much information. And furthermore, that can change. So this talks about creates an empty list, or returns the element at the specified index of the list, and so on. Now, we just did an exercise when we went from the abstract value to the concrete value and back. When you implement MyList, you know you need to set the instance variables to values that represent the empty list. At that point, you've got to do that exercise we just did. You've got to figure out, okay, how should I set them to represent the empty list? And of course, we set count to 0, and we've got to set data to something that is at least 0 big, and we choose to make it 10 just in this implementation, so there's room to grow. And you have to convince yourself, okay, if I have an array of length 10 and a count of 0, does that represent the empty list? And the answer is yes. That's what makes that correct. Right, what about the get method? So first we make sure the index is in bounds. If it is in bounds, how do we know that you can, that if I want to get element 5 out of the list, that all I have to do is get element 5 out of the array? How do we know that works? What about our representation strategy tells us that that will work? Say a little louder.
It's because index is equal to count minus 1.
No, we don't know index is equal to count minus 1.
I mean, well, size of the array.
Yeah, so okay, that comment says the elements of the list are stored in data 0 through data count minus 1. And I should have said more. They're stored in the right order. So element 0 of the list is stored in element 0 of data. That's what that says, and that's why it makes sense to return what's ever stored at the given index of data. The indices in the list correspond to the indices in the underlying array. Okay? And they're set. Same deal. If you want to change what's stored at a given index of the list, you change what's stored in the given index of the array for this particular representation strategy. Okay? This adds to the end of the list. And this is where we got our efficiency. We say if the count is data.length, then the underlying array is full, and we've got to make a copy that's twice as big. Now, once we have done these first two steps here, this step here, have we changed anything about the list that we're representing? So if we leave count the same and just copy the data into an array that's twice as big, after we have done that blue block, is the list that's represented by the data and the count the same as the list that was represented when add was called? Yeah. Because all we did was make a copy twice as big. We didn't change count, and we didn't change the first count elements in the array. They're the same. All right, now that we're sure there's room, we say data sub count gets val, so we're adding that new value at the next available spot in the array, and then we're incrementing count. And at that point, Once we've done those two things, now our list looks like it has an extra element in it, because the array has an extra element in it now, and count's been incremented. But you can't do any of this unless you understand your representation. All these methods have to be consistent with, they have to consistently use the instance variables. Now if we go back to plain old MyList, you'll see it's simpler. To create an empty list, we just create an empty array. To get an element out of a list, we just get the element out of the array. Same thing with setting and then adding. To add, we make an array that's one bigger and then we store to it. Both of these implementations are correct, even though the code is completely different. Why is the code completely different in the two cases? What's the important difference between the two classes that requires the code to be different?
Efficiency.
Well, efficiency was the motivation. But where in this class do you look to make sure that your code works? What's the key difference between the two classes?
Where it copies the array.
Well, yeah, the copying is important. The doubling is important. But I'm going to say this is what's important. The representation strategy is completely different. Now, suppose I took this representation strategy for the first version of MyList, and I went over here, and I replaced all this with that. It doesn't work, does it? And if I go the other way, things won't work either. Okay? It doesn't work because there's no count instance variable anymore. You can't just, so what happens if you go the other way? And paste this into version 1. There are no compiler errors. But what's wrong with this implementation? In fact, if you ran this thing against tests, it would pass all the tests. But I would still argue this is incorrect. Why is the implementation incorrect? How is it? Yeah, it's incorrect for no other reason that it doesn't, it says up there that count is always supposed to be the number of elements in the list. But none of our code is updating count here in version 1. So you need to be consistent with your representation strategy. So let's think about the cache class. Your cache class, every cache object, when you call the constructor, you pass in the name of the class, of the cache, the owner's name of the cache, the difficulty rating, the terrain rating, the code, and maybe something I've forgotten. And then there are methods to obtain from a cache object its code or its owner or its title. So if you were to open up a cache object, what would you expect to find inside? Yeah. You expect to find instance variables, and probably the simplest way to represent a cache object is by having one instance variable to hold the title, and one instance variable to hold the owner, another instance variable to hold the difficulty rating, and so on. And you have the constructor to set those instance variables, and then you have a bunch of methods to extract the information. But you've got to, before you try to write any code, to fill in the stubs, you've got to pick a representation strategy. And sometimes you'll find that you pick the wrong representation strategy, and you're not able to implement the methods. You've got to go back and come up with a better representation strategy. It takes some time to get used to that, but it's a different sort of programming. So the first part of the class was all about, of the course, 1410, was all about control structures. So loops and conditionals and return statements and so on. Now we assume you've got that nailed, and now we're turning to a different, very different idea. How do you create types of data that were never there before? Let's take a break and we'll explore this some more. All right, now, I'm going to switch gears a little bit here. I'm going to make my first attempt at suggesting to you what's happening inside the computer's memory when a program runs. And that might also give you a little added insight into how objects work. So down in the lower right are the relevant portions of the MyList class. So you can see this is version 1. So I have that data array, and then I have the constructor, which creates an empty MyList. And to do so, it sets data to be an empty array, as we just discussed. And I'm going to animate for you. Look at the very top. Imagine there's a main method somewhere that's executing this statement, MyList list equals new MyList. So it's creating a new MyList and storing it in the variable called list. So let's see what's going on. So there's a region of memory that Java uses to store the values of parameters and the values of local variables, as methods are called. And that's called a stack. So when you look up things on Stack Overflow, for example, that term, Stack Overflow, comes from the stack that exists in memory when programs are being run. And Stack Overflow is when the program runs out of stack memory, and that causes the program to crash. And the stack grows as methods are called. So initially, there's no space being taken up on the stack. As methods are called, the space used by the stack increases. We'll have it increase from bottom to top. And then as methods return, the space shrinks. And I'll show you what I mean by that. The stack is divided into frames, and a frame corresponds to a method call. So each frame keeps track of the values of the parameters involved in a method call, and also the values of local variables. That's just where they're stored. So let's say we have a main method, and it calls f. So I'll go back here. We have the main method. That'll contain all the variables, the local variables main needs. If main calls f, then a new frame is pushed onto the stack to keep track of the variables for f. Now when f returns, it disappears from the stack. Now maybe main calls f again, and f calls g, and g calls h. So each time there's a method call without a return, the space on the stack used by the stack increases. And if you look inside those frames, you'll just find variable values stored in there. And then as you return, again, the space shrinks. So that's what the stack is for, is to keep track of variable values. And when I say variable values, I mean parameters and local variables. So let's see what happens when we call that method new MyList. So I've created, that's the stack frame for main. So I'm not even showing you main here, but main contains a variable called list, and we're trying to set the value of list to be this object that we're creating right there. So main is calling the constructor. So when you say, well, let's just see what the next step is here. What happened there? So we're in the middle of trying to execute new MyList. And so the value of what we did first was the new part. When we create a new MyList, first thing we have to do is create space in memory to hold the object's instance variables. There's only one here, data. And then that becomes the value of list. So list refers to that object. Now, that object is not on the stack. It's stored in another piece of memory called the heap. So the heap contains objects. Right? So first step in calling a constructor is just to create the raw object that you need. What's the job of the constructor? What's the constructor do to that raw object?
It initializes how much space it's going to take up in the resources based on how many variables.
Well, you started by saying it initializes. So yeah, it's going to initialize that data variable. So we got to call the constructor. So to call the constructor from the main method, remember this is the stack frame for the unseen main method. It's about to call the constructor. We'll have to push a stack frame for the constructor. Now, what variables does the constructor? So here's the constructor. There are no local variables. How many parameters are there? Well, there's 0 if you don't count the implicit one. So the constructor has an implicit parameter. It's the object being constructed. And so what's going to happen is we're going to push a stack frame for the MyList constructor. It'll have a variable called this. To what will this refer? In that diagram right there. What will list point to? I'm sorry, this. What will this point to? It's going to point to the object being constructed. Where is that in my diagram? Yeah, here's the object right up here. So I separated the two stack frames just so you could see it better. So we push a stack frame for the constructor. It contains the one thing, this, and then we set its value. This is what Java is doing as part of the constructor call. It sets things up so that this is referring to the object that needs to be constructed. Now, the code inside the constructor can run. And what's it going to do? What's going to change about the picture up there when the constructor runs? Is it going to change what list points to? Is it going to change what this points to? Well, what's it say it does? It says this.data gets an empty array as its value. So what would you expect to change about the picture? All right, I won't make you guess any longer. What it does is the constructor goes, oh, this.data. So it goes to its stack frame, this. It goes to its stack frame, it finds this. It follows the arrow, and that gets to the data field. Okay? And then we store in that object a new empty array. So it just looks like that. So now the data refers to an empty array. Then the constructor returns, and we're left with that picture. Now, before the constructor returns, notice that this and list both refer to the same object. When the stack is popped, because the constructor returns, we still have, we still are keeping track of that object via list. So we're back in the main method. Now, let's suppose now the main method calls list.add of 5. And now you see the code for add. So what's the first thing? What is the stack frame for add going to look like? What's the stack frame for add going to contain? How many variables will be in there? Parameters and locals. No local variables. How many parameters to add? 1 plus the implicit parameter this. So to prepare for calling add, a stack frame is pushed to hold the values of val and this. Well, what is the value of val going to be? This is the method call we're making, list.add of 5. Right. So 5 is the value of val. What's the value of this going to be? So the 5 comes from right here. Where does this come from? Right here. So val's going to have a 5 next to it. What's this going to point to? It's going to point to the same thing list points to. So that's method. That's called method call linkage. You're just setting things up for the method call. So now when the code for add runs, it's looking at its stack frame. So let's see what it code says to do. It says, okay, you need to go find this.data, and it can. It just follows the error out of this. to the object. It finds the data field in the object, and it says I got to make a copy. And that actually is another method call that I'm not showing you, trying to keep things simple here. So it creates a copy that's one bigger, and then it says that copy becomes a new value of data. So how do we make that copy become the new value of that data field in the object? How should our picture change?
Point to the new one.
Yeah. So that's what Java is doing as it runs. It's using this data structure, running around doing what the code says to do. And then it says, okay, go to that thing, the data field, to the array referenced by the data fields, and store val as its last element. So it'll just watch what happens here. It just goes up there and stores a 5 in it. That's what the code says to do. But really what it's doing is it's going, okay, let's go to this. Let's go to the object. Let's find the data field. Let's go to the array. Let's store a 5 there. So the code that's actually running is sort of going around following references, setting a value. Now we're done with the add method. What's going to happen with that stack frame? It goes away. Well, okay. So I made that bit go away. That old array we don't need anymore. That's the technical term for that is literally garbage collection. It doesn't necessarily disappear right away, but when Java needs more space in the heap, it goes finds garbage objects and reuses their memory. So I'll just do that to keep our picture clean. The method returns, the stack frame goes away, and now we're back in the main method. So at any given time, lots of frames on the stack, but only the one at the top is the only one we care about at any given time. That's the one that the current method is using. Let's add 9 to the list. What's going to happen? We're calling an add method from main, so we push the stack frame. Okay, what's the value of val this time going to be? 9. And the value of this is going to be a reference to that object. And the same thing happens. We go make a copy of the array referenced by data and store that as a new value of data, like that. And then we start at this, we go to data, we go to the array, and we store a 9 in it. That thing's garbage. Method returns, so its stack frame disappears, but we're left behind with the object that we're trying to create. Okay, what happens here? We're calling list.set. How many parameters to set? 3. The 0, the 2, and this. What's the value of index going to be? First parameter is called index, so 0. The value of val, the second parameter is going to be 2, and the value of this is going to be what? Same thing list refers to. Then we just go and change the thing at index 0 so that it's a 2. Then we return. And so from the point of view of main, list has changed. All right, that's just your first look at stack and heap diagrams. You tend to see them over and over again as you move through the program. So I think right now it's a pretty foreign concept to you, but I want to introduce it to you right now. So when we revisit it, you'll have seen it at least once. Okay, now we've been, that's new stuff, but pretty much we've been reviewing. Let's look at another class now. So we created a MyList. Let's create a MyMap. So right here, look at the main method. It talks about how a MyMap would work. So you can create an empty map with a constructor right here. And then you can, we're going to have the keys and the values always be strings to keep this simple. So here I have put Utah as the key, and it has a value of 4. So this is working like a hash map or a tree map. If we print out the size at this point, it should say 1. There's one thing in the map. Then we associate Ohio State with 1, and we associate Utah with 3. I think when I made this example, the Utes were going up in their football ranking. Ohio State was number 1, and Utah kept going up, but okay. What's the size of the map at this point? 2. Because we have, when we set Utah to 3, its value changed. There are 2 keys with 2 values. Now, there's going to be a get method that will give me back the value associated with the key Ohio State. So what would that print out? 1. And the next line would print out 3. And then there's a remove method to remove a key. So Utah loses, they fall out of the top 25 or whatever. We take them out of the map. Now the size of the map is 1. So that's what we want to create. We want to create an object with those methods that behave like we expect maps to behave. So let's look at what methods there are. First of all, there's a constructor that creates an empty map. And then we have this method here that if key is already in the map, then it will change its value. Otherwise, it'll add a new association to the map. Remove just takes a key and its value out of the map. It does nothing if it's not there already. We can extract the value by key, and you can get the size of the map. So we need to implement those methods in that constructor. So we understand the specification. We've looked at some examples. Maybe we've written some test cases. I have some test cases I've written. What's the next thing we need to do? Okay, if you've retained one thing from today, I hope it's this. What is the first thing you need to do when it comes time to implement a class like this? Yeah?
The representation stuff.
Right, the representation strategy. You've got to decide how it is you're going to make this thing behave like a map. Now, what's the obvious thing to use as your representation? To make this super easy to implement. What would you have inside each MyMap object? Yeah?
Hash map or tree map.
Yeah, hash map or a tree map. Okay? But that's no fun. So let's assume maps don't exist. So we've got to decide some way to keep track of the keys and the values so that we can remove and get and size and so on. So help me out. What instance variable should we have? Yeah. We could have an array. What would be in the array? Okay, you said 2 smaller arrays. So we, rather than have an array that contains 2 smaller arrays, let's just have 2 arrays. Okay? So we've got the proposal here that says we're going to have 2 arrays. Should it be the same length? Okay, we'll make our 2 arrays the same length. Now, someone else tell me, if we do it this way, what's the point of the 2 arrays? Yeah?
One for keys and one for values.
Okay, so maybe we'll call one keys and one values. All right, now let's suppose that right here we have Ohio State as a key. And let's say the value of Ohio State is 1. Where should it go? Directly underneath it. So if the key is, whatever is stored as the key in location 0 of the keys array, its value will be at location 0 of the values array. Okay? This is all part of making our plan. And if we put Utah here as there, then maybe its value will go there and so on. Okay? Are we going to allow empty space? Are we going to have our arrays be exactly the right size? Okay, it's the same trade-offs as when we did a MyList. Let's say we make them exactly the right length. What happens when we go add a new key? You've got to copy both arrays, make them one bigger, and put the new key there. What happens when you remove a key? You're going to have to, like if we remove Ohio State, we're going to have to shrink the array by 1 and make sure we copy Utah over to location 0. We could make that work. But I'll allow you to use something a little more powerful than an array. Yeah, let's use an array list. That'll take care of the growing and shrinking for us, so we don't have to worry about it. So rather than using a pair of arrays, let's use a pair of array lists. Same idea. That way we don't have to trouble ourselves with what happens when the array fills up. The array list won't fill up. Okay, so that's our representation strategy. Let's play around with it before we write any code, though, to make sure we understand what we're doing here. So that's my list. Okay, there's my map. So there's our representation strategy sort of spelled out. So we have an array list called keys, and the comment says the keys of the map in no particular order. And there are no duplicates in the list. You can't have duplicate keys. And then for the values, it says the values of this map has the same length as the keys list, and the value associated with the key at index I is the value at index I. So that's pretty much what we said, right? So let's play this game. So let's say the keys are A, B, C, the values array contains X, Y, Z. Okay, what does A map to? X. What does C map to? Z. So I'll write it that way. So that's those pair of lists represent the map that maps A to X, B to Y, C to Z. Okay? What map is that? Yeah, that's the empty map. There are no keys and no values. Okay? What about that? Keys are A, B, C, the values are X, Y, W, X, Y, Z. That's a violation of our representation invariant. We said that you couldn't have that. Right? So that's illegal. Your code should not produce that situation. Okay, so you got to be able to play these games before you try to write any code. Let's see if we can write some code. Once you understand your representation, then you can write each method in Constructor without worrying about the others. So what will it take to create an empty map, my map? We have these two instance variables. I need to declare them, so hold on a second. Notice I make the instance variables private. Why? Why are instance variables private? So you can change them, right? Once they're public, then the code, your client code, can depend on it. Sorry about this. Great. And I should put the comments in there, but I don't have time. They're in the slide. What do we do in the constructor? We've got to initialize the instance variables so that they represent an empty map. So we've got to go from the abstract back to the concrete. So what combination of values and keys represents an empty map? Yeah?
They both need to be empty.
Say again?
They both need to be empty.
Right. We need empty. New. And same thing for values. Okay. So keys and values. Each is a separate empty array and empty list. Okay. Now, let's go to an easier one. Suppose someone asks us, what's the size of the map? How many key value pairs are there in the map? How do we answer that question? What should we return? What's that? Right. We could return keys.size, for example. Could we return values.size? Yes, because our code is going to make sure they're always the same length. It says that in our comment. Okay, let's add a new element. Let's add okay, so we're going to associate the key with the value. Now there are two possibilities. Either the key already exists or it doesn't. And what we do depends on which is the case. So we need to find out if the key is already in the map. If it is, then we just got to replace its value. If it's not, we got to do something else. So how can we find out whether the key already exists in the map? Right? We got to look into the keys list, right? Let's see what we got. I like index of. You'll see why in a second. So we're going to ask, what is the index of that key in the keys list? So if what we get back is negative, we know that it's not in there. If it's 0 or positive, not only do we know the key is in there, but we know where it is. So let's do the two cases here. What do we do if index is greater than or equal to 0? Meaning the key already exists. We just got to update its value. What is it that we need to do? Yeah?
Replace the value at index with the new one.
So we need to do values dot set at the index val. So we don't have to touch the keys array. The key's already in the spot. We go, let's say it's in location 5, index 5. We go to index 5 of values and store our new value there. And then we're good. And the reason we know that works is because our representation strategy says that's how it's supposed to work. What do we do if the key does not appear anywhere in our keys list? In other words, it's not part of the map. Yeah?
Add it to the array list.
Right, we just add it to the end. So add will add to the end, so we'll add the key to the end. Are we done? Right, we got to also add to the end of the value. So, if I just showed you that in isolation, if I said, oh, here's a method, did I implement it correctly? And all you knew was that there were instance variables called keys and values. You could not tell me whether that was correct or not. What is it? What knowledge is it that lets us conclude that is correct? Besides, we got the specification, we got the code, but what else do you have to know to convince anyone that is correct? Okay, go ahead.
The representation.
Right, the representation strategy. You have to know what the representation strategy is to judge whether that's correct or not. Because if I can change the strategy completely. Now, no, that's no longer any good. It's got to be consistent with the representation strategy. We will continue with this next time, finish this up, and then we'll look at a completely different way, a different representation strategy for the same thing.